So let's talk about polynomials. So we're going to be interested in polynomials with the following form. Now, I must stress that there's more polynomials than just these, but I will stress and I will give you a hint for how we can generalize the rule I'm going to show you here shortly. So consider the form P of n. So this function is going to be called P. It's going to have coefficients. The first one's going to be called a0. It's going to be multiplied by n to the k plus a1 times n to the k minus 1 plus a2 times n to the power of k minus 2 all the way down to a sub k minus 1 times n to the power of 1 plus a k n to the power of 0, which this right here is just 1, right? If you want to rewrite this in terms of summation notation, or you want this as a sum, it just looks like this. The sum from I is equal to 0 to k. So this is just representing each one of the terms. I'm just going to vary it over I. So I'll start off with I is 0, then I go I is 1, then I is 2, then I is 3, all the way up to I is k. You'll notice that this is actually just what I've written up here, is as follows. It's ai times n to the power of k minus I. So notice that when I is 0, you end up with a0 times n to the power of k. When it's 1, then you end up with a1 times n to the power of k minus 1. And when you put in k all the way at the end, you end up with ak times n to the power of k minus k, which is just 0 like we have over there. So this summation will be helpful for us for when we prove our claim here in a moment. But I must stress that these things, these multiplicative constants out front, these are called coefficients. Where coefficients a0, a1, all the way up to ak, these are all going to be non-negative, meaning that they're allowed to be 0 or positive. So I must stress that there's a way to generalize the approach I've stated as earlier. So I'm gonna give you an approach for dealing with these kind of polynomials, and I'll tell you how you generalize the argument so that these are allowed to be negative. But I must stress it's still a complexity function, so the function still has to be as we defined it earlier. But like I said, the reasoning is very simple. So like I said, you can have it where the coefficients are negative, but with just a small tweak of the argument I'm going to give you here, it's very easy to generalize. So the lookalike approach actually spells out an actual technique for dealing with polynomials that look like this. So do you know how we played lookalike, right? We had it where, okay, we tried to make it so we grouped the terms based on each polynomial, like each one of the terms that I have for the polynomial, and I tried to express it in that way, and I just added up those, and that's how I got C, right? That's actually the technique you could use with dealing with polynomials. So here's the theorem. So given constant, and I must stress that for this proof, k is going to be an integer constant. It's going to be k is greater or equal to 0. But I must stress, by the way, that there's other ways you could also demonstrate that this also can be a real constant. But the proof I'm going to give you here only relies on it being integer based. But like I said, there's properties out there you could easily extend this idea further. If you're curious about this, let me know. And the above coefficients the claim is that P of n, or P, well, I'll just refer to as P here. P is big O of n to the power of k. That's the claim. So we're going to prove this claim now. And before I get to that, I want you to imagine that each one of these coefficients is like a light bulb. And I have a switch that I can use to include it or not include it. So keep in mind that any polynomial that I've given you in the past fits this form. You just have to pick out the constants for each one of the coefficients, right? So for example, earlier I gave you an example. I had 4n to the power 4 plus 3n to the power 3. We had 2n to the power 2, and I just had n, right? Well, notice here that if you make k is equal to 4 in this claim here, you'll notice that this is actually going to have the same form, with the exception that I have nothing for the case of n to the power of 0. But wherever I have gaps like this, you can think of it like I'm turning off a light switch. But it isn't just any old light switch. It's a one that's variable, that I can control how much flow goes through. So you can imagine every time I toggle the switch on, it actually takes on the value of each one of these coefficients. So just like what we talked about earlier, when I pick out and I try to play lookalike, this is actually the same way this is going to play out. So let's do the proof here. So you're going to see that this bucketing approach I gave you in the past actually easily generalizes here. And you'll see very quickly that all of our examples are actually just special cases of this. And like I said, I'll give you a tip on how you would generalize this a little further, and I will have that proof in my notes. So, as usual, I give you the game plan. So we find constants. We find constants c, that's a positive real number, and n0, which is a positive integer, right? We find these two constants such that for all n greater or equal to n0, p of n is less than or equal to c times n to the power of k. Okay, so now I'm going to show you how I'm going to pick the constant. Now remember, all I did when I played lookalike with you earlier, in earlier examples, what I did was I looked at the coefficients of the polynomial and I just distributed the terms on the right-hand side to make them look like those ones, right? But what are those terms? Well, they're the coefficients of the polynomial, right? So I'm just going to pick c is equal to be a0 plus a1 plus all the way up to ak, which this is going to be equal to the sum from I is equal to 0 to k of ai. So I'm just going to take all those coefficients and going to add them together. And now remember, the way I picked the n0 before always ended up being 1. That's not a coincidence. It's because this actually is the case. It's going to be the case here. Then observe that for all n greater or equal to 1, well, let's write out what p of n is. P of n is that sum I have over there, right? The sum from I is equal to 0 to k of ai times n to the power of k minus I, right? Well, notice that every one of these terms, these n to the power of k minus I terms, as I gets bigger, it always makes this term smaller or equal to whatever n to the power of k is, right? So I'm going to do the same trick I did before. So watch this. So 0 to k, the sum from I is equal to 0 to k of ai times n to the power of k. So I'm just going to drop the minus I business. I'll just put a k right there. And then this is equal to the sum. So notice that all of these n to the power k's, they don't vary with I, right? So I'm just going to put it out to the side of the summation, and then look what you got sitting inside of here now. I is equal to 0 to k of ai. So I got all of this, then I multiply this by n to the power of k. But what's that? What's this? That's c, right? That's c, exactly. So, but remember, this isn't enough. I have to still argue to you why this is the case. So you're going to notice very quickly that I can use the same set of reasoning that I did before, except to generalize this now. Now I have to do it over all of these terms inside the sum. I have to do it for each application of I. So I is 0, I is 1, I is 2, I is 3. But whenever it is the case that that coefficient is present. So when it's the case that ai is 0, I don't want to do this because you know that it's just going to be 0 versus 0, right? So as ai times n to the power of k minus I is less than or equal to ai times n to the power of k, well, notice that if I divide both sides by, well, let's take a look at this. We have k minus I, and I have a k there. Notice that if I take this and I chop off enough needed to make it so that that side over there, because I could divide both sides by ai, right? Because it's okay, because they're both going to be either, they're going to both be, well, if I presume they're not 0, right? This is very important, is that they're positive. So if they're both positive, I can just drop these, right? They could go away. Then I had n to the power of k minus I is less or equal to n to the power of k. Well, look at this. If I take this and I divide both sides by whatever will make it so that I end up with a complete picture of this, in particular if I divide both sides by k minus I, if I divide by k minus I, in this exponent here. So remember, if I divide by k minus I here, with both sides, n to the power of k minus I divided by n to the power of k minus I is 1, right? So that means that n to the power of k over n to the k minus I, you should end up with whatever is left after you subtract off k minus I, right? But what is that? That's just I, right? Let's just check that for ourselves. Just some side work here. Let's see. K minus, so if I have k minus I, okay, k minus k, these two are going to go away, but I have plus I left. So yeah, this will end up being just I here, right? So that means that this is going to be 1 is less than or equal to n to the power of I. But this is for all 0 is less than or equal to I is less than or equal to k with, so we want the ones where the coefficient is not equal to 0. And it is the case that this is for n is greater or equal to 1. If you actually look carefully at what I wrote here, this is just the exact same set of reasoning I've been using when we talk about bucketing the terms. The same exact idea. Make no mistake, this is the exact same kind of reasoning we were using before. I just divide the sides so that I could get the bigger one on one side, right? That's what I did every single other time, at least if you wanted to whittle it down further. So, choose n0 is equal to 1. Therefore, by the definition of big O, P is big O of n to the power k. And we're done. That's it. Surprisingly simple, right? It's surprisingly simple proof. It's just that it's actually just all of the things we've been doing up to this point thrown together into one cookbook way of doing things. So if you ever run into a polynomial with this form, you just simply add the coefficients. Now, you might say, Dan, what if my coefficients sometimes are negative numbers? Say, for example, like A2 is, say, -2 or something like that. Well, I'll give you an idea of how you do this. Well, the way this argument will work is that instead of it being where you just simply take each one of them separately, you'll take the absolute value of each one of these. And you'll notice that this argument actually just doesn't change a whole lot. So if this is p of n, so you have this, notice that putting the absolute value will make it either that if it's negative, it's only going to get bigger, right? If I drop the sign, it's always going to be positive. And then you'll end up with this right here. And you'd make an argument very similar to the one we had down here. But I will not go into those details too much here. But the general rule is, if you're dealing with polynomials, you just take the absolute value of each one of the coefficients separately, you add those together, and then you could pick n0 to be equal to 1. Piece of cake, right? So that proof will be in the notes.